So, good afternoon. My name is Nitin Jogalkar, and I'm your host for this afternoon. And we're going to start just a couple of minutes earlier because we have such riches of ideas to present to you this afternoon. Um, the first session is being hosted by my colleagues, Professor Paul and Professor Kulatilaka, and they're going to talk about their vision for R&D and education at Boston University. But part of the Boston University vision is a new institute that just got inaugurated on our campus. The institute is called iTech, and it's my great pleasure to actually invite the new director of iTech, Jonathan Rosen, to just introduce himself and tell us about his vision.
Thank you. Good afternoon, everyone, and I'd like to start by complimenting the organizers for a wonderful conference, and I'm learning a lot, and I'm sure you are too. The Institute for Technology, Entrepreneurship, and Commercialization, as Dr. Jagdekar said to you, has just been started here at the school. It's built on a long and proud tradition of teaching entrepreneurship program started by my colleague who's here with me today, Peter Russo. The new institute is based here at the School of Management at Boston University and is a resource not only to the whole university community, but also to the larger community in Boston, nationally and internationally. Our mission is to provide education and training in entrepreneurship, and we do this through a number of programs that are both degreed and non-degreed programs. We offer executive training as well as diploma programs and custom programs for companies, for entrepreneurs internationally that come here and study for periods of time from a few days up to a full semester. And of course, we offer a concentration in entrepreneurship as part of traditional MBA programs in several different fields. So if you would like to learn more about us, please look at our website. It's bu.edu/itech, I-T-E-C. And congratulations and enjoy the rest of the meeting. Thank you.
Good afternoon and welcome back. Now you'll get to hear the research and educational activities in the College of Engineering and the School of Management in the area of clean energy. I'm Uday B, and after me, Professor Nalin Kulatilaka will be presenting. I have to go through a lot in this presentation, so in terms of the number of slides. So I may not be able to go through all the details in my slide. So the presentation is going to be online. So if you have any questions, you can email me or call me, and I'll try to answer. If I'm not able to, I will have my colleague, the right person to answer the question. Okay, the mission is to study and innovate means to generate, use, and manage a sustainable, clean energy future that will satisfy all our energy demand, preserve our environment, and allow economic growth. And as you can see, all aspects of energy, starting with selection of the energy source, to the way we generate, we store, we distribute, and consume, can have profound impact on the local, regional, and global environment and economy. And I'm sure we are going to hear more about all these areas during the last session or the panel discussion. So I'm going to start with what we at Boston University, we do have a clear advantage in terms of clean energy research and education. And you can see out here, the College of Engineering, the School of Management, and the College of Arts and Sciences, we have clean energy research and education being conducted in all three programs. and these are synergistic and complementary in nature. This allows us to really engage in much larger and more meaningful research collaboration that not only addresses new technologies, but how to market the technology and also to assess the societal impact of the technology. It also provides the opportunity to the student in each of these programs to learn from the other programs and get a much broader and more complete education in this important area that is clear to influence the future generation. Oops. Let's see. Now I'm going to, from this slide, I'm going to talk about the research, the major research activities that we have in the College of Engineering. We start with our activities in the area of fuel cells. We have come up with a manufacturing process that involves one sintering step to manufacture the solid oxide fuel cell. And this we are doing with our industrial collaborator, BTU International, and Don is sitting in the audience. We have used this process to make high performance solid oxide fuel cell at a very cost-effective way. Here is the microstructure and the performance of the cells. And it allows us, if this process we are able to successfully scale up, then it will allow us to bring down the cost of manufacturing fuel cell, solid oxide fuel cell stacks by an order of magnitude and help the solid oxide fuel cell achieve commercial realization. In the area of membrane technology, we have developed an oxygen ion and electron conducting membrane that can be used in a membrane reactor. Steam is going to be fed on one side of the reactor and fuel on the other side of the reactor. The oxygen from the steam is going to be extracted by the membrane, and it will be used to oxidize the fuel on the other side. So the end product is going to be hydrogen that will be coming, or the steam is going to get converted to hydrogen, and the fuel is going to be oxidized. We have used these membranes that were developed in our lab, and we have been able to get flux on the order of 13.4 liters per meter square per minute of hydrogen. And this rate is sufficient to power small low temperature fuel cell systems based on polymer electrolyte fuel cells, where having ultra pure hydrogen is the major challenge. And this technology will enable us to do that. In the area of hydrogen economy or enabling hydrogen economy, we are working with Safe Hydrogen on using light metal hydrides as hydrogen storage media. So what we do is essentially to release the hydrogen, we react the hydride with water, and hydrogen is released. The objective of this program is to come up with a system that has the right gravimetric and volumetric energy density that is required by the transportation industry. And at the same time, to come up with a recycling technology for the byproduct to meet a cost target, which is 2010, it is $4 per kilowatt hour, and 2015, the target is $2 per kilowatt hour. So in the area of green processing, we have developed a process where we are using a solid oxide fuel cell to electrochemically split the metal oxide and generate the metal with the byproduct oxygen gas. And this we are using to synthesize and produce energy-intensive metals like magnesium and titanium, tantalum, so on and so forth. Here is a schematic of the setup for the production of magnesium from magnesium oxide. The magnesium oxide is dissociated. We get magnesium metal in the form of a vapor, which is condensed in the reactor, and the byproduct oxygen gas, it comes out of the solid oxide fuel cell. We can generate this magnesium as very small particles in fact, we can make it nanocrystals of magnesium, which will give, which can be used for energy storage applications as well. And in this process, the energy consumption is 10 kilowatt per kilogram of magnesium. And if successful, if you can scale up, the estimated cost is 30 to 40 cents a pound of magnesium, and which is 50% the cost at which the magnesium is produced today. In the area of bioenergy, we have heard the waste to energy conversion by Scott. So here we have a similar process that allows us to convert the biomass or waste to energy. And the way we do that is we again use membrane technology. We have steam, we feed steam and biomass, and we employ some electrical energy. The steam is split, and the oxygen from the steam, it's transported through a membrane to oxidize the biomass. And on the steam side, we end up with pure hydrogen. And on the biomass side, we oxidize the biomass, and we end up with syngas. And both the hydrogen and the syngas can be used for the fuel cell applications. Another area of bioenergy is building novel batteries. And here what we do is, here is the conceptual representation of the process, and we use microbes as catalyst to oxidize the biomass at the anode and generate hydrogen, which then migrates to the cathode and is oxidized to water. So here you can see the laboratory scale setup. This is the performance plot that shows the stability, the long-term stability of such cells. Here are some performance figures, and it can use any type of a carbon-containing source, and the potential applications could be bioimplants, remote sensing, robotics, and I don't want to say this, but it can be used to generate power from you know what. Oops, okay. So another area we are working on is advanced coating systems, and another way to impact clean energy is by increasing the processing temperature of the power generation technology. In this case, if we can employ gas turbines at higher operating temperatures, we can improve the process efficiency as per the second law of thermodynamics. So this we can do by applying improved thermal barrier coatings. And we have developed a real-time feedback control strategy for plasma deposition of thermal barrier coatings. And we control the variables in the plume to engineer the cracks in the coating in order to improve the lifetime and the performance. So as we increase the operating temperature of the gas turbine, we also become, the turbines also becomes susceptible to corrosion, environmental corrosion. So we are also developing environmental barrier coatings. And here in this slide, you can see such a coating which is a functionally graded molite deposited on a silicon carbide substrate. And you can see when the coating is not present on the surface gets attacked by the environment, which in this case is slag, and you can see the formation of the pits. And by having even 1 to 2 microns of the coating, you can see that the substrate is adequately protected. Oops. All right, so we also have an ongoing program at Boston University on energy efficient solid-state lighting involving LEDs. And as you know, the solid-state LEDs, the solid-state lighting involving LEDs, they have significant potential in terms of improving the conversion efficiency of electrical energy to optical energy, producing white light. It's possible to get efficiencies on the order of 50%. And with 50% efficiency in the solid state lighting, you can get energy efficiencies which are 2 times more than fluorescent lamps and 10 times more than incandescent lamps. The research activity at Boston University is directed at developing gallium nitride-based LEDs with the capability of a very high photon conversion and extraction efficiencies. And the research is also directed at bringing down the manufacturing cost of these LEDs. And one way is to develop an inexpensive gallium nitride substrate by hydride phase vapor epitaxy instead of the more expensive MOCVD route. Here is a spectrum of the BU's phosphor-less white LED based on textured nitride multiple quantum wells. All right. As you heard this morning from Professor Karamanis, we are also employing systems theory and network science to facilitate the penetration of renewable technologies like the wind to electricity. And this is done by combining and optimizing various means to overcome the limits or market barriers to entry. And I'm not going to talk much on this anymore because you heard about this in the morning. We are also in the process of starting a few new programs. In this slide, we are starting a program which involves design, fabrication, and systems integration of microfuel cells. And we are using our expertise in the area of MEMS fabrication and fuel cell technology to develop this program. We are also working on micro energy harvesting devices based on piezoelectric material, which converts its mechanical energy into electrical energy, and it can be used to power biomedical implants and wireless sensors. So in short, what we have is we have a set of core expertise, and we use this core expertise to branch out into different areas of clean energy. And with this, I'm going to have, I'll ask Nalin to tell us more about the School of Management.
Thanks, Uday. Fortunately, I don't have as many pretty pictures or animations to use, so let me show you the pictures that I have. I'm using an excuse to come up with something. So the basic premise of most of what the management school's research hinges on is the fact that the choke point for adoption is not innovation in technologies, but rather impediments to adoption. Some could be regulatory, some could be organizational structures. But in particular, a couple of themes of research that we are working on recognizes the fact that the greatest impediment to adoption is in fact the existing capital stock that we deploy. The houses we use, the way our communities are designed, the infrastructure that we have built, and so on. So this is to motivate you even more to say that this is not a new problem for mankind. We've dealt with this with all kinds of other technologies and ecosystems built around it that involves hardware components, software components, skills, behavior patterns that we have all built around. So it takes a lot of time from the introduction of an idea to its maturity. And so this is the basic point I did. And in order for that to happen, what we're trying to bring about is a way for adoption to get to a point where systems could be tipped. And and I'm going to give you a brief survey of some of the work that's going on, not necessarily at the moment in the energy sector, but we've gleaned a lot of tools and instruments and expertise in other sectors that we are beginning to bring to bear in the clean energy sector. One of which is the study of complementary network systems, which started, which is led by Professor Venkatraman in the School of Management under the research institute called BUILD with a large number of member companies. And we've been looking at the adoption of a number of information technologies. And a particular tool that he's used, and I'm going to use one set of examples that he's developed looking at the video game industry to see how the game consoles and the various content, the various games that were built around it, have evolved over time. And what his studies have done is, in fact, to come up with a mapping tool that allows us to visualize the landscape of how this ecosystem evolves around companies. And that's led to a number of studies, one of which has been to understand the economics of what makes a company, what makes a strategy work for one of these hubs, in this case Nintendo and Game Boy, I think, Xbox, to switch from one standard to another. So there's a few more of these pretty pictures. And an interesting point that he's made in this last one is, in fact, there comes a point that it doesn't have to be necessarily the standard around the hardware that makes it switch, but it could be, in fact, the kinds of games you use on these standards that would make it switch. And there are some interesting general lessons that we might be able to glean from these studies which could be applicable to the energy sector. For instance, it doesn't have to be the energy generation or the distribution of the storage, but it could begin from the energy use devices or the organizations that are built around it. A second set of work drills deeper at how the users respond to new technologies. There's a number of studies done on that, and the one that I'm going to focus on is one that's led by John Henderson, and it's a part of a study called the Connected Home Project. And under this project, we have a number of industry partners, one of whom is already here. It's from Actus Lendlease, who you'll hear from in just a few minutes. This study involves 2,000 or 3,000 houses in a number of Army bases around the country, which have been connected with modern communications technology. And it's been used as a living laboratory to understand how end users, in this case families, respond to these new technologies. And the applications, in fact, I have one slide on that. So here are the 6 bases in which the homes have been deployed, the technologies have been deployed. And we have studies that involve education, healthcare, communication, and more recently now in energy management. So for instance, if you install a particular kind of heating system or a cooling system or an appliance, in order to estimate the benefits from it, the energy savings, for instance, would require a good understanding of how the end user really deploys it. And this is an experimental platform that allows us to study that. We have a number of other projects or research areas, which I'm not going to go into too much detail given our limited time, which I've listed here the titles of the research areas and the principal investigators or the research faculty in charge of that. R&D R&D investment models. That's a project that we are looking at investments into early stage technologies and how the different organizational structures would impact the way R&D decisions are made, from startup firms to all the way into national laboratories which have national interest at heart to larger companies with research divisions. So how that organizational structure impacts the R&D investment decision. We have people from our marketing department and organizational behavior looking at the notion of corporate social responsibility. Some of you probably have heard a lot about the research going on here. There's a sense about trying to understand whether doing good and doing well are related to one another, and there are studies on that. We have a number of projects in the finance group. Most notably, the one I want to talk about is valuation and portfolio management. And this is a project that Professor Stewart is running through a number of our programs, one of which is our Master of Science in Investment Management program has students working on creating portfolios and analyzing firms, and the energy sector is one of the sectors that he's got students working on. We also have undergraduate projects where students follow portfolios and write analyst reports on these companies. So it's an opportunity to have our students be involved in these. And finally, I wanted to use the fact that I have the podium to talk about some of the stuff that I'm doing with Martha Amram, who's already alluded to some of these points. And the idea is the notion of an energy intermediary that could, in fact, be brought in to harness some of the opportunities that are arising from the introduction of these new technologies. So we first heard the lack of an intermediary as an impediment. So if you turn it around and think of the way to capture that value as being the intermediary. So let me give you a 2-minute version of that. So if you think about the current model being one where electricity is generated, transmitted, and distributed to customers, and typically the utilities do this and the customers bear it, and if it's residential customers, this is really the model. If it's an industrial customer, you might have an energy service company that sits in the middle. But if you take it to the next level, which is the one that we might see in some places, there are these energy service companies who step in the middle between the utilities and the customers, who might begin to manage the various risks that the customer or the utility was facing before. And by pooling across customers, these risks would be transferred and managed better. So the idea is, can we think of a new organizational structure, a new entity, a new player who could parcel the risk out to different people better? And here's a concrete version of the idea. And this applies also to the demand side story that Mike Karamanis was mentioning at the end of the morning, which is if you have an intermediary that provides energy services to a pool of customers, and of course the energy services and energy saving technologies, conservation technologies, the initial investment would be funded by an outside lender, and the servicing of these loans would be carried out by the savings that would accrue over time. But those savings that you would accrue needs to be measured and monitored and verified independently. So this creates a role for the cyber infrastructure that Mike was alluding to, that somebody needs to measure and monitor this and almost create a currency around which contracts could be written. And this, we think, is a new potential business model that could emerge. Just as a closing point, this is not really something new because, in fact, I would argue that this is something like this has been happening in the information services outsourcing problem, which is kind of like you have large companies, a new set of intermediaries that have emerged originally as system integrators and subsequently as outsourcing companies that do something like this. So just as a quick sum up here, here's a list of things, and this is once again going to be on our websites for you to look at. What I want to do next is to turn it back to Uday to talk about how we plan to wrap all of this research happening around the university in the form of a research center. And Uday would say a few words.
Okay, as it is evident, we found out that we have a large number of activities that are going on in the university in the area of clean energy. And it involves the two colleges, College of Engineering, School of Management, and the College of Arts and Sciences. So we are proposing to create a clean energy center. And the idea is with the large number of faculty and students involved in research in this area, we will be able to use the center as a springboard to launch highly visible research programs that will lead to marketing of next generation technologies. We can also use the center to disseminate knowledge in this area by conducting seminars, workshops, and by interacting with an industrial consortium we hope to have in this center. And at last is we are also going to use the center to train students and postdoctoral fellows in areas of energy efficiency, energy conversion, environment, marketing of technologies, and the societal impact of the different technologies. And with this, I think I would like to end this presentation. It leaves maybe a minute, and if you have any question, I'll be happy to. If not.